very particular honor and pleasure to be invited to speak in this conference in honor of Greg. So, so today I'd like to discuss a few things about double dimers and some, in a sense, very classical but quite beautiful and maybe not so well known in these circles notions from integrable systems and how these relate to combinatorial limits. So I'm going to start with. Is it? Yeah. It should. Oh no, it's actually not. No. It is?
Yeah.
Okay, so.
No, you switched up. No.
It's okay?
Can you move it closer to your
So, is it on or? No. So maybe speaking louder is working. Okay.
It's higher. Yeah.
Okay, so thanks. So after this interlude, let me start with kind of explaining the poem. So setting the poem. So first, dimers. So I'm going to which are, I guess, quite well known by many people here. So there's some underlying graph which has to be planar, and there could be a few variations, but I'm going to take a square lattice or a finite portion of the square lattice, and a dimer configuration is a selection of edges in such a way that each vertex is going to be adjacent to exactly one edge in this selection. Okay, so I just pick a certain number of edges. And then I can play the same game and take another configuration which is going to have the same property. So I'm going to use another color. It's going to look like this. Something like that. So now if we consider the superimposition of these two configurations, what's going to come out is a bunch of cycles like this and a bunch of doubled edges. Okay, so now in the double dimer model, what you do is just you select independently uniformly both the blue and the yellow configuration, and you get a gas of non-intersecting loops plus a bunch of doubled edges. So you can play slightly different games, and instead of taking the two configurations on the same graph, you can take slightly different graphs. So I'm going to take a big square now. And I'm going to take a blue dimer configuration which is going to be on this square. Something like this. And then I'm going to take a yellow dimer configuration which is going to be uniform but on the square minus these two opposite corners. So in which case, what I'm going to get is a bunch of closed loops. And because I've got these two excisions, I'm going to get on top of these loops a path which is going to traverse this square. Okay, and a conjecture which is due to Rick is that this guy is going to converge to SLE4. In the limit where the square is fixed and you take the mesh to 0. Okay, so in particular to support this conjecture, something which follows from, again, Rick's work on convergence of the dimer height function to the Gaussian free field is the following. So if I select a point Z inside this domain, I can look at the probability that Z is going to lie below this discrete curve. So you take Z to be, for instance, the center of a face in this square lattice. So it's either going to be below or above this random curve. And this, it's in the limit where the mesh delta of the lattice goes to 0, this is going to converge to something which is harmonic on your domain, so which would be a square or something else. So I'm not going to discuss all boundary conditions for now. So it's going to be and H is going to be the solution to the Dirac problem where, so simple Dirac problem where you take Dirac boundary condition 0 on the top arc, 1 on the bottom arc, and you extend harmonically inside. So that's going to be the limit as delta goes to 0 of this, which from SLE technique we know is the same that what we have for SLE4.
Is it obvious why they should be harmonic?
So it's not actually discrete harmonic. So that's the point. So it converges to something which is harmonic.
Is it even obvious why it should converge to something harmonic?
Well, so if you separate both configurations, right? So each configuration is going to have a corresponding height function, which is going to converge to a free field. This free field is going to have a mean which is harmonic because it's a free field. So the difference of these two harmonic functions is again harmonic as simpler boundary conditions, which are these boundary conditions. So yes, so that's a corollary of convergence to the Gaussian free field of each separate dimer configuration. Okay, so when you look at this, so one of the many very influential ideas of classical paper by Greg, Oded, and Van Lin on the loop random walks is the martingale observable method, which was deployed to prove convergence of loop random walk to SLE2 and uniform spanning tree Peano exploration path to SLE8. In which case you have something which is kind of similar, where you have an observable, so which is, the event or something condition on your path, which is going to converge to something, to corresponding quantity for SLE. And if you can do it dynamically for all domains, then you're in pretty good shape. So somehow, if you could work out not only that the probability that Z is going to end up below that path, but also the probability that it's going to end up below that path conditional on this initial exploration slit, then you would be in very good shape to get convergence to SLE4. Unfortunately, this result is kind of dependent on the precise choice of boundary conditions, and this choice is not stable under exploration. So what's believed is that it's, in a sense, statistically stable, and this is very related to the kind of like massive technical issues that Oded and Scott faced when dealing with level lines of the discrete GFS. In which case you have actually the exact same limit, and you also have statistical, in a sense, stability of boundary conditions, but not exact stability of boundary conditions. And if you actually went through that paper, you see that it does make a difference. Yes. Pages and pages and pages of them. So that's kind of where we were. And I guess a couple of years back, so Rick again came up with a breakthrough and introduced a new class of observables. So again, in this, it's actually not, in a sense, an observable of the double dimer configuration. You have an observable of one configuration and an observable of the other configuration. So these guys are basically decoupled to get the 1 point observable. So now it's going to look like this. So now I'm not going to look at this picture. I'm going to look at the picture as above. So I'm going to look at a big domain and then sample 2 dimer configurations, and I'm going to get a bunch of loops. And then then what's conjectured is that the relevant limiting object is going to be the conformal loop ensemble with parameter 4. And so now we are going to add spectator points. So like Z was just a choice of point in this domain, I'm going to choose a certain number of points and maybe branch cuts toward that are going to connect these punctures to the boundary, and then choice of matrices. So a certain number of branch cuts, a certain number of fixed matrices. And then the object is the following. So for each loop, so each loop is going to be oriented, and to each loop you're going to associate a number, which is the following. So first, so these red guys are punctures, so I'm going to look, so a way to encode this data is to look at the fundamental group of D, which is my total domain, minus this puncture, so this is a free group, and then choose a representation of this free group in SL2C. So this is equivalent to choosing these matrices once you fix the branch cuts, and when you take a loop, each time you cross a branch cut, you're going to multiply by this matrix or its inverse depending if you're crossing in the right, in the right orientation or the opposite orientation. Yeah. So maybe I should have put loops like this also. So given each loop, so given each loop, you associate a matrix. So for instance, this loop, you're going to get A3 times A2 up to cyclic permutation. And then a number which is a trace of this matrix. So this matrix, so this trace does not depend on the choice of root. So if I'm starting there or there, it's not going to matter because it's just going to cyclically permute this trace. So you get the same trace. And if you reverse the orientation, it's also going to be the same because I'm in SL2C. And the trace of a matrix in SL2C is equal to the trace of its inverse, just by writing it. Now the man kind of the main result again due to okay, so I'm going to comment on this. So the main result of freak is that you have a combinatorial expression of this, of the expected value of this class of observable. So you're going to look at all the loops in your loop configuration. For each loop, you're going to add the factor trace rho L divided by 2. And then that's going to give you the determinant of some explicit linear operator.
This is with some x's put down that's before you put the loops down.
Yeah, so the red guy is fixed and then you average over the purple guys. So the red guys are just fixed paths on your dual lattice. So these are just branch casts, so you choose your branch cast.
Yeah,
So a variant, and then you sample your purple guy like this, and you average over this guy. Okay, so if you take most, of course, it's going to converge. Well, I mean, if you're going to have many small loops at small scales, but any loop which does not cross two, okay, so any loop which does not cross a branch cut or cross back immediately is going to give you rho L equals identity, 2 by 2 identity matrix, in which case this factor is 1. So basically the only thing which is going to contribute to this product are A, loops which are macroscopic and cross at least 2 branch cuts, and B, loops which are macroscopic but are around one single puncture. Okay, so yeah, so maybe I don't want to get into actual details of how this is done, because then I would spend all my time about it. But if you don't have any row, what you get is a partition function of your model, because you have 2 independent configurations. Yeah, I should have divided by. Yeah. Yes, right. So if I take expectations there, I should divide by my partition function. Okay, so a classical result of Castelline from the 60s is that the partition function of one dimer configuration is the determinant of a linear operator, which is a nearest neighbor finite difference operator, explicit. which is useful to think as a discrete version of d over dz bar. And then you have two now copies of your dimer configuration, so now you can think of d over dz bar operating on 1 by 2 or 2 by 1 vector valued function. And then you're going to twist this by this character, or not this character, this representation rule. So the moral picture is the following. So, I mean, in the continuum, you can look, there's a well-defined operator where you just look at nice function from d to c square. So, let's say some subole space of function from d to z square, and then you take d over dz bar, component by component. So, that's a reasonable operator. And then now you're going to modify this picture by saying that instead of looking at nice function from d to c square, you're going to look at functions that have jump discontinuities across branch cuts. So if this branch cut corresponds to the matrix A, if you're going to have 2 points, you're going to approach a point on the branch cut from the top and from the bottom, then you're going to have a linear relation between these two guys, which is going to be your jump matrix across the branch cut. And then it's easy to see that if you displace the branch cut, then you're just going to conjugate your operator. So, I mean, the actual position of the branch cut is irrelevant. Okay, so now kind of issue is, so what I guess I want to actually discuss is convergence issues. So I mean, how you make this moral picture actually exact. So now I should also said that again one of the main results of Rick in this line of work is to show that you have a conformal invariant for this purple picture in the sense of laminations. So in a sense, the main problem is to identify the limit at this stage. And also, I guess the main, philosophical interesting point here is that instead of having a single dynamic observable, which is a martingale observable method, which was pioneered by Greg and Oded and Van Lin, and then exploited by Stas, Smirnov for percolation and easing, in which case you have a single observable which you can control on a family of domains. Here what's fixed is a domain, and then you have a whole lot of observables, because you can choose your punctures and you can choose your representation. So you have a basically countable family of observable in a static domain. And this is more or less a way to circumvent difficulty with instability of boundary conditions for dimers, which is the main difficulty here. Okay, so now So now if you start looking at this picture above with this matrix jump boundary condition, it's a very classical story on which there are a lot of tools we can use. So going back to Riemann, so that was actually basically, Riemann was Hilbert's student, and that was his thesis. Riemann-Hilbert problems. So yeah, so I'm going to maybe remind you of one of Hilbert's problem, which is, I think, 21st, which has to do with monodromy representations. So it goes like this. So you take the Riemann sphere, and then you make a bunch of punctures on this Riemann sphere, and then you consider the following equation. So actually not the same as before, but still matrices. So that's a differential equation in a complex variable. Okay, so you think of y as being either 2 by 1 or 2 by 2. I mean, it could be higher dimension, but we're going only to use it in dimension 2. So this is a differential equation in holomorphic vector valued or matrix valued function of a parameter z. So z is a point on your sphere, a's are fixed matrices, so this is a linear differential equation. So away you have singularities at the punctures. And then there's a normalization condition, so sum of ai is going to be 0. So you can solve this locally by standard Cauchy-Kowalewska type of result. And then what's useful is to fix normalization at infinity. So you're going to take the solution, which is metric valued and is equal to identity at this point at infinity. And because of this normalization condition, if you change variable at infinity, you see that it's perfectly nice at infinity. Okay, so what happens is the following. So if you take your solution y0 at infinity, it starts at identity, and then you know that in any small ball, you can continue your solution. There's no obstruction to continue analytically continue your solution along a path. And then you're going to come back to infinity. And when you do this, you're going to collect some monodromy matrix. Okay, so that's a well-defined thing. So it doesn't depend. It's going to depend, of course, of the homotopy type of the loop. But if you deform your loop continuously, it's not going to change this matrix. And what you're going to get is a representation of the fundamental group of C hat minus functions. So it's not hard to see that if you do two loops in a sequence, then this is going to multiply nicely. Because if I'm looking at this equation and then I hit it from the right by a fixed matrix, I'm going to get another solution. So rho is a so-called monodromy representation. Okay, so I'm starting basically from analytic data, which is a nice first-order ordinary differential equation, and I'm going to get out of it algebraic data, which is a representation of the punctured surface. So, slightly different way to phrase it is the following. So I'm putting GL2. If you take the S to be tracelets, you're going to get SL2, so that's not really important. Okay, so you start from this data, so this fixed matrices A, you put them into this ODE, you do this analytic continuation business, and you get rho, which is a representation out of it. So that's a well-defined map, and then essentially the 21st Hilbert problem is to decide whether this map is invertible, which is given representation rho, can you come up with these matrices such that your representation comes from this analytic data. So it's mostly true, right? So in a sense, I mean, it was solved in kind of, I think, the 60s maybe, and then it was disproved in the 80s, and then solved again. So the thing is that...
Is this the 21st problem, or is
yeah, I think it's 20, yeah. Well, I mean,
yeah,
it's one of them.
This is the problem.
Yeah, so that's the problem. So, I mean, the problem is, well, at least, right, to find, you know, given a representation, show that there exists, yes. And then there, I mean, it's a bit slightly more complicated. Well, I mean, there are nuances where, depending on what type of singularities you allow for your equation. Okay, so in a sense, I mean, it. So actually, I mean, the argument, I mean, for a long time, the argument was more settled, but assuming without loss of generality that at least one of the A's is diagonalizable, in which case it's solvable. But actually, there was loss of generality, and I guess Bollybrook in the 80s figured out that when none of the A's is diagonalizable, there are counterexamples. So when you have like each of the A is, for instance, a pure Jordan matrix, you can set things up in such a way that the problem is not invertible. But this occurs only in dimension 4 and above. So I can, like, simplest example involves 4 by 4 non-diagonalizable matrices. Okay, so
I'm confused. I thought the problem was to find the A's from the row.
yes, and it's not, yeah, right.
So how can that problem was with no condition?
So
AI.
so yeah, so So it's known that if at least one of these is diagonalizable, you can no. No, so that's not. Yeah, thanks. One of who was. Yes. So one of the monodromy matrices is diagonalizable. Then you can invert it. Yeah. Thanks. Okay. Yeah, it's demanding to. You also have to do like the proof checking for the talk. It's a pretty thankless test, but it's still the beginning of the week, so right. Okay, so now there's another. Okay, so in our case, solvability is not going to be an issue because anyway these are 2x2 matrices, and B, we also construct the solutions we need. So so another part of the theory, which is also largely classical, was kind of revived in the 80s, is okay. So I'm going to try. Is a problem of so-called isomonodromic deformation, which is the following. So you're going to have your punctures, and now you're going to start moving them. And the basic observation is that if you just move the punctures a bit, then you can identify the fundamental groups. You're going to choose a set of generators. As long as your punctures don't cross one of the set of generators, you can keep the same generators. So now your data looks like this. So you have okay, so given a choice of lambdas and a choice of a's, you have a monodromy representation, and you're going to start moving the lambdas. Now the problem of isomonodromic deformation is how should you adjust the a's such that rho is fixed. Yes, that's very, in a sense, self-explanatory terminology. And there's a condition for this. Which is again early, kind of like pre-World War I, the Schlesinger equation looking like this. So now, so the a's are fixed with respect to the z, which is this variable in my OD. But now I'm going to move the punctures, and I'm going to take the a's as being functions of lambda. Of the punctures. Okay, so it's kind of condition you can, in a sense, work out if you work with it, is that a necessary and locally sufficient condition for preserving monodromy is that you're going to take this derivative. So when you're going to adjust the a's when you vary the lambdas, you're going to take this partial derivative, which is expressed in terms of the bracket ai j. So this, these are coupled. So this is for all I and j. So these are coupled non-linear equations. So it looks a bit scary because just knowing that you can actually solve them simultaneously. So in a sense, the explanation of this equation is the following. So you can extend this equation. So on top, as the punctures were fixed, and I was moving z. And you can extend this. So if I take this normalization condition y0 at infinity is equal to the identity whatever the puncture location is. So this is going to be true for all punctures. Then I'm missing something, which is y0. So then you can solve simultaneously for z and the puncture. So you can compute the derivatives of your solution with respect to z, which is this variable, and the location of the punctures. So total derivative of y0 is given by this expression. So this is a way to say that d y0 over dz is exactly what I had before. D y0 over d lambda 1 is minus a1 y0 over lambda 1, or z minus lambda 1, and so on. So these are all the partial derivatives of y0 when I move simultaneously z and the punctures, given that my condition normalization at infinity is given.
AI is a function of lambda here?
And so now AI is the function of lambda, yes.
Yeah.
Right. But now, so for this to make sense, so for this to be solvable, you need integrability condition, and this integrability condition are the Schlesinger equation. So the fact that this equation is solvable boils down to this condition. And then, yeah, I mean, the fact that this solution, once you know that this is actually solvable, then isomonodromy is basically true property. I mean, you can.
Right, so the AI of lambda in that equation is the solution to the Schleck.
Yeah. So this gives you all the partial derivatives of y0.
Yeah. So yeah, you.
Yep. And the AI is for this to make sense, have to satisfy that equation. So this is just kind of Pfaffian integrability. So if you have
The condition that makes the partials.
yeah, right. So yeah. So when you have
What works? No.
again, so there's basic integrability condition when you have, for instance, a system of the following form. So if you have simultaneous partial first order differential equation, so if you want full rank solution, if you want, so z is the unknown, b1 and b2 are given, are functions of x1 and x2. So if you want solution, you can work out the following, that you want the Clairaut relation, right? So, and this you can compute by differentiating top with respect to x2 and bottom with respect to x1. And this gives you a consistency condition which looks like this. So db1 over dx2 minus db2 over dx1 is like bracket of b1, b2. And conversely, if you know this is a zero curvature condition. If you know this, then you can solve this locally. Simultaneously, these two guys are an open subset. So if you do this, instead of having x1, x2, you have z, lambda 1, lambda 2, lambda n, and so on. You work out what these Pfaffian integrability conditions are. These are the Schlesinger equation on top. Okay, so this is again, so that's the classical theory of isomonodromy, and then so now in the 80s, Sato, Miwa, and Jimbo, in the well-known work on holomorphic quantum fields, introduced a new object, which is the so-called tau function, which is going to be which is the following. So you start from this isomonomic data. So you have this A satisfying the Schlesinger equations. And given this A, you're going to construct a function which is now to depend only on the position of the punctures. So rho is fixed. And then given rho, you're going to decide that the partial derivatives of tau have to satisfy this question, and of course missing the lambda minus lambda j. So this records all the partial derivatives of log tau. So for this to make sense, you need cross derivative conditions, and for the cross derivative condition to be satisfied, you're going to end up again with the Schlesinger equations. So highly non-trivial. I mean, if you just try to come up with nice functions, having prescribed partial derivatives, it's not so clear, but so that motivation from easing to come up with this function. So now this is a function of what? So it's a function which is in a sense defined on the space of A moduli space of punctured spheres and B equipped with a monodromy representation, and then that gives you a number, essentially. Okay, that's it. So now kind of trying to wrap it up. Okay, so if we go back to the picture we had, like this, maybe let me do it in the upper half plane. So we're in the upper half plane. And then we sample a double dimer configuration in the upper half plane. And then there's a certain number of branch cuts, which are arbitrary, and then I've got a representation associated to this. Okay, so I've got, so again, we had this formula, which is but this expectation is given by a determinant, or ratio of determinants. So then the construction is going to look like this. So in order to transpose the standard theory, which is defined on the sphere, to something in the upper half plane, as usual, you just do by doubling. So you're going to just double all your cuts, and then that's going to give you a punctured sphere with twice as many punctures. And then the claim is that as the mesh goes to 0, this is going to converge to the tau function, which is associated to this data. So you double the punctures, now you have a monodromy representation of the sphere. That gives you a tau function, which is going to be the limit of this observable. So there are some conditions which I'm going to list. And then the second claim, which is in a sense completely disjoint, is that this function is actually the same thing that what you get for CLA4. So for CLA4, you have a well-defined object which has a bunch of loops, and for these loops you can compute the same quantity, and you see that this quantity is actually this same tau function. So convergence of this to this and equality of this and that are basically two completely disjoint sets. So again, so the issue we had is the following. So or one issue that you got to deal with at some point, and I guess you can deal with a couple different ways, is that around each puncture you're going to get many small loops, and all these loops are going to contribute factors there. And to keep things nice, you want these factors to be 1. So basically you want all these basic monodromy matrices to be unipotent. So this is
sorry, the tau function is defined on the upper half plane or on the sphere?
so to define, it's originally defined on the sphere, right? And then to extend this definition to the upper half plane, you just proceed by doubling. So yeah, so you double this picture, and then now you use definition on the sphere. Okay, so I mean that's actually okay. So it's a bit, you've got to be a bit careful, but yeah. Okay, so again, in order to circumvent the issue of small loops giving you some blow-up, it's not going to happen if your basic monodromy matrices, which are the ones that you collect when you cross one cut, are unipotent. So you take them to be of this form. But of course, they don't have the same basis in the Jordan normal form. But that's actually quite a bit of information. So using this and also arguments by Rick, you can see that if you fix 2 points, if you look in your loop ensemble, the number of loops which are around these 2 points, then this is a well-defined random variable under this measure, which is going to converge in low to the same variable for CID4. I mean, it's kind of interesting because CID is maybe not the most kind of computable object. So 5 minutes to kind of so what are the issues? So I'm going to comment briefly on this, and then even more briefly, I guess, on that. So statement C. So if your punctures are actually on the boundary, then nothing happens because you have expected value of 1 is equal to 1. Okay, so if you start from the boundary and you start moving the punctures, you just need to see that this relation is satisfied. I mean, keeps stays correct when you start moving the punctures. And when you start moving the punctures, you have exactly an isomonodromic deformation problem. So you start moving the punctures, you keep the fixed monodromy representation, and then you have this bunch of formulas coming from the Schlesinger equation and this tau function, which tells you what happens when you move these punctures. Okay, so this tells you what happens to the tau function when you move the punctures, and what happens to this thing when you move the punctures. Then, well, I mean, it's a dimer computation, so it's kind of manageable. So typically what you end up dealing with is the following situation. So you have discrete holomorphic functions which are multi-valued in such a way that when you cross a branch cut, you multiply by this matrix. So typically you're going to have functions which look like this. So if this is 0, you're going to have discrete holomorphic function, I mean a multi-valued function around this branch cut which has this type of jump is going to look like this in the continuum, and in the discrete you need to replace log of z by a discrete logarithm. And then when you do this, well, I mean, you just I guess what I used to do is open intersections of random walks, and what I'm doing now is open random walks, a modern introduction, and then you have all the estimates you need to deal with this kind of holomorphic, discrete holomorphic logarithms. So you need, okay, so that's basically to deal with what happens to this quantity when you move a function. Other side of the story is to actually identify this in terms of CLE4. So for CLE4, basically you want to compute something which is maybe not a good idea, and yeah, so you need some sort of effective computable description of CLE4, and then going back to Scott's idea about exploration of CLE4, basically you're going to start from the boundary and start making these small excursions. And then you're going to, well, I mean, there's some limiting procedure, but if you somehow manage to catch one loop which is close enough to the boundary, you can go around it, and then you're in more or less good shape if you start doing it again. So there's this picture where you're going to start exploring your CLE4 by trying to catch loops from the boundary and see what happens to this quantity when you do this. So once you start on a loop, you're in a kind of like more stable picture, which is the type of picture where you have a kind of variant of CLE4 where you have one embedded chordal path which is going to be an SLE4, and then two CLE4s on each side. So once you have this, so if you're in this kind of picture, and again I'm computing in the continuum, now you can do this SLE type of exploration where you're going to explore that guy dynamically. And then you're back to martingale arguments. So you need to figure out a deformation of this quantity where you're in the situation where you basically, for instance, essentially you're conditioning to what happens if somehow there's a loop which hugs the boundary for a long time. So it's something like that. So you need to deform this observable to accommodate for this insertion. Once you can do this, then it's just basic martingale arguments. Well, I mean, yeah, straightforward enough. And so this is going to be expressed, so it's not I mean, again, the tool for this is to go back to this formula we have. Which gives the total derivative of the fundamental solution of this differential equation in terms of the position z and the location of the punctures. And we had the complete expression of this for these guys. And now this z is going to be the seed of your SLE. So this z, which we had rotating around the puncture, is now going to be the seed. And then under the SLE deformation, the z is going to be displaced, the punctures are going to be displaced, and I know all my partial derivatives. And then it's a simple enough computation to see that what you get is going to be kind of what you can figure out should be the answer in this variant of the model. So this variant you could also get by taking not, as I said before, not the same underlying graph, but you take one graph and one graph minus two vertices, and this creates one CLE and one SLE and two CLEs. in which case we can figure out what the answer should be in that situation and check that it works for CLE. Okay, so I guess we need to stop there.
Yeah, maybe just one question because we'll get to that.
So actually, I was looking at this one where I was bang on time, but that one is for the record. Yeah, I mean,
Can you work out this expression? I mean, what the function is for other values of kappas?
yeah. So I mean, so what? No, I mean the answer is. But that equation. So it's like you have this sporadic martingale, and I mean there's some like extents of I think maybe like Kalu or someone knows more about this, but you have some some sporadic martingales which work for exactly one value of kappa, and which you cannot deform. So yeah, I mean it's kind of interesting. So yeah, maybe I mean you need new ideas to deform this. But yeah, I mean if you look at nature of the object, so you have observables which depend on punctures and representation. So it kind of functions on a kind of complicated space. So yeah.
Okay, so maybe we'll give enough questions of the technique.